Hey everyone, I'm a core engineer at SDF, and today I'll be talking to you about our work on BucketlistDB, a next generation database for blockchain applications. So today, I'm going to start by talking about the current implementation of databases for blockchains, both at Stellar and at other blockchains. Then I'll talk about some of the issues with those blockchains, in particular, how they don't scale very well. Then I'll dive into the details of our new database, BucketlistDB, and end with some experimental results from our first test runs. Now, as I'm sure all of you know, the Stellar network has grown significantly over the last couple of years. And as we add more users and more transactions to the network every day, the state of the ledger is increasing. The state of the ledger includes all the ledger entries that are necessary to make the network run. These are things like offers, trust lines, and accounts, all that sort of stuff. And as you can see here, the amount of these ledger entries has grown exponentially over time. While today, the database is currently not a bottleneck for network performance, if this trend continues, then we will need a new database very soon. Especially with the introduction of Sorbonne smart contracts coming up soon, we expect not only the number of ledger entries to increase, but also the size of the ledger entries to increase, as we add new ledger entry types, such as smart contract data and smart contract code. So what is the issue with blockchain databases today? Well, first let's talk about how they work. First, we have a standard key value store. Now at Stellar, this key value store is SQL, but many other blockchains use other non-SQL methods. For instance, Ethereum uses something called BucketlistDB. And this key value store, or SQL, carries the entire state of the ledger. During consensus, we do many reads to this database. For instance, say Sally wants to send 10 XLM to John. We need to load Sally's account, see that she has 10 XLM in that account, and then decrement that from her account, and then add it to John's account. These are all key value lookups. Now, even though this database contains the entire state of the ledger, it alone is not good enough for our applications. Because we're building a distributed, decentralized blockchain, we need to have a proof that this database is actually correct and holds the correct values. To get that proof, we use hashes. Now, every ledger close, the Stellar ledger header includes a hash of the database in order to verify this data structure. Now, to generate this hash from a SQL database, we would have to iterate through all 46 million ledger entries, hash each one individually, and then take the hashes of all those hashes. Now, Stellar closes a ledger every 5 seconds, and so this operation is significantly too expensive to do. And so in order to make this more efficient, we have a second duplicate data structure called a Merkle structure. Now at Stellar, we use something called the bucket list as our Merkle structure, but many other blockchains have this same problem with duplicate data structures. The key value store and the Merkle structure contain the same entries duplicated in 2 separate places, doubling the disk required to run a validator. Now, the idea behind the Merkle structure is that you can hash more efficiently by saving hashes you've already calculated and only rehashing entries that change. So in our example, when Sally sends John 10 XLM, in the Merkle structure, you'd only have to rehash the accounts that changed. So instead of having to rehash all 46 million ledger entries, you'd only have to rehash John's account and Sally's account. Now, we need these duplicate databases because while the SQL and the key value stores are good for point loads and for loading individual keys, they are not good for generating hashes. And while our Merkle structures are good for generating hashes, they are not good for key value loads. To understand more why the bucket list is not good for key value lookup, let's talk a little bit more about how it works. So the bucket list is a pretty tricky data structure. So I'm going to start with a simplified version and then flesh it out as we go along. So as you can see here, this is a general diagram of the bucket list. It's similar to a log structured merge tree, where essentially you have these levels that contain these buckets. As you go down in levels, the size of the bucket increases exponentially. Essentially how this data structure works is we only ever write to the topmost level of the bucket list, the smallest bucket. Whenever that bucket fills up, its entries then spill over and are merged into the bucket below. Because we're doing this spilling and merge operation, all of these buckets are also sorted. Now, to kind of illustrate this a little bit better, let's use an animation. At the beginning here, you see we have an empty bucket list, where every bucket is empty so it has a 0 hash associated with it. We then will begin writing elements to the topmost bucket. After these elements are written, we then hash that bucket and save that hash for the bucket. Now, because this bucket is full, we now need to merge it down the lower level. So we'll merge it down, and we see how now the lower level maintains the same entries and has that hash. We'll continue writing to the topmost level where the input is, and then again, hash that bucket as well. When that bucket is full, it too will be merged down to the lower level. Now, because we're doing this merging, and because every single level has a hash associated with it, it's very efficient to generate a hash of the entire data structure. Instead of hashing every single entry individually, because we have our buckets that already have a hash, we only need to combine those hashes, and we are able to produce a proof of the entire database. Now, there's a couple details here that we should explain a little bit further. First, we don't actually store the real ledger entries. We don't actually store accounts, offers, trust lines, or anything like that in the bucket list. Rather, we store changes to the ledger. So a ledger entry could be an initialization. Say we create an account, we would write an initialization event to that top level bucket. If an account is updated, we would write an update event. And if an account is deleted, we would write a delete event. So while we're not really actually storing the individual ledgers, we can still deduce what the ledger should be based on these updates, initializations, and deletes. Additionally, I think I need to define when a bucket is considered full. A bucket is considered full not when it has some amount of ledger or some amount of entries into it, but rather once a certain amount of time has passed. This is measured in ledgers. So for instance, the smallest bucket, the first level bucket, would contain 4 ledgers of information, whereas the second bucket would contain 16 ledgers of information, and so on and so forth. In this way, the bucket is not full when some number of transactions have been applied, but rather once a certain time period or a certain amount of ledgers has passed. Now, one of the key factors in the bucket list structure is that whenever we need to do these merges, or whenever we need to do these hashes, whenever the entries spill over to the lower level, it happens instantaneously. Now you might be wondering, how can we do the merging, and how can we do this hashing instantaneously? It's almost like magic. The key is whenever we need to do a merge or whenever we need to do a hash, we do it well in advance on a background thread. To illustrate this, here's a more in-depth diagram of a bucket list. Now, in this bucket list, we see that it's been running for a while, and so it's more full. Now, in order to have the hashes and the merges prepared preemptively, what we actually do is instead of merging right away to the lower level, we have a snapshot bucket. So here we see the buckets in blue are our current or our hot buckets that we actually actively write to, whereas the gray buckets are our snapshot buckets. Now whenever, as you see on the level 0, the current or the hot bucket is full, we don't immediately merge to the lower level, but rather we take a snapshot and we move those elements to the snapshot bucket. Now once a snapshot bucket has been populated, we then immediately spin up a background thread that you can see here in the dotted oval. That background thread will then preemptively create a new bucket, which is the merge result of that snapshot and the level below it. By doing this preemptively, we can have the hash and have the merge ready well in advance. And so as you can see on the background thread, we already have the merge result ready and prepared. In this diagram, there aren't hashes just omitted for clarity, but we also hash it in advance as well. Then we will continue writing to our topmost level bucket like we were before. And now we see that both the hot bucket and the snapshot bucket are both full. So in this particular instance, we now need to spill over. So what we do is we take that bucket that's already been created and we just place it in so it can be instantaneous because it was built in advance. Then we empty the snapshot bucket, the hot bucket entries turn to the snapshot bucket, and the process continues. One important clarification, I've used some terms like move, copy, etc., and we actually don't move any of the elements. In order to be efficient, the files remain constant, and we just do some pointer arithmetic and move pointers around. So even though in the diagram we've had entries moving left, right, blocks moving around, in actuality the files stay constant and we just move pointers around. So the high-level key takeaways from the bucket list data structure is that we can achieve very fast writes. Because the main thread only writes that top-level bucket, we can actually do writes on the data structure with no disk I/O operations. Because the top level is so small, we can actually fit the entire bucket into memory. And so the main thread can write without ever having to go to disk. This is very important when it comes to write amplification. It is one of the key problems with Merkle trees and Patricia tries used by other blockchains. For example, the Patricia trie is the Ethereum version of the Merkle structure. For that structure, you have to do many disk I/O rings that scale with the size of your ledger. So as your ledger grows, the cost of each insertion also grows. But because we've structured our bucket list this way, we can always have constant time, immediate, fast writes, and never have to block for I/O writes. Additionally, this data structure gives us a very fast hash of the entire database, so we don't have to iterate through or do an inefficient operation. However, this data structure has very poor read performance. Because the elements are distributed among the different levels, we don't know what level an element is at if we're searching for it. So for instance, if we have a key and we need to find the value, we must iterate through every single level of the bucket in order to find it. These buckets can be very large. The lowest levels are sometimes 5 to 10 gigabytes large. And so we cannot search efficiently for these values. So going back to our current database structure, we have our key value store SQL, and we have our Merkle structure, the bucket list. Now this is clearly inefficient as we're doubling the disk usage required. But there are a couple of other issues as well. What we need to do is essentially get rid of one of these extraneous databases and pick one and see if we can convert it into the primary and only data structure. Now, when choosing between these two, we need to think about which is kind of like the primary or root data structure. It turns out that we use our bucket list more for just the hashes. As I mentioned before, each bucket in the bucket list records a certain amount of time. Whereas the top level bucket contains the first 4 letters, second bucket, 16 letters, etc. Now because each bucket actually records a time period of history, we can use the bucket list to do peer-to-peer catch-up. If you imagine a situation where you have 2 nodes, one of which has been turned off for a while and then turns back on, the validator that has been turned off will be out of date and will not be at the same ledger close as other nodes that have been running on the network. So in order to catch up, we can compare the bucket list of the running node to the bucket list of the restarted node and take the delta difference. In this way, the bucket list gives us a very efficient method of catching up to neighbors in peer catch-up situations. Now, because the bucket list is used both for this peer catch-up and for creating the Merkle hash for ledger closes, it's the primary data structure. And so whenever a validator turns on, first, it compares its bucket list to the bucket list of its peers around it. After then repairing the bucket list and catching up to its peers, the bucket list then copies its entries over to the SQL database. This copy is very expensive. If you recall, the bucket list doesn't actually contain entries, but rather changes to entries. Because the SQL database contains actual entries, whereas the bucket list contains only changes, to actually convert the bucket list entries to a SQL entry takes many, many writes, as you have to write changes after changes after changes, instead of writing an account entry just a single time. For this reason, it's very inefficient to rebuild the SQL database, and the SQL database is not very practical for our use cases. So what we decided to do was to remove the SQL database entirely and use the bucket list both for hashes, peer catch-up, and for key value lookup. There are also a few additional problems with SQL that make it unfit for our needs. First and most obviously, the ledger entries are redundantly duplicated, both in SQL and in the bucket list. But secondly, SQL itself is actually not very well suited for bucket list read-write operations. The way that the Stellar consensus protocol works is we do many reads during consensus, and one single atomic write to the database on ledger close. Now, our SQL implementation that we use on most validators is Postgres, and Postgres is ACID compliant. Now, what ACID compliance means is it has overhead protections to make sure that reads never interfere with writes. However, for our purposes, because we know we will never write when we do a read, because of the way consensus works, this ACID compliance is unnecessary. Additionally, SQL cannot take full advantage of parallelism. Similar to the ACID compliance issue, during consensus when we're doing all these read operations, the database is immutable and unchanging. And SQL cannot fully take advantage of this fact. So our solution to this problem is to turn the bucket list into a searchable data store. But as I mentioned before, it's a very bad data store, so we have some work to do. There are 2 key issues. First, we don't know what level an entry is at in the bucket list. And second, even if we know the level, the buckets can be very large, and we don't know where in the bucket an entry is. So we need to solve these 2 problems. So first, let's talk about where to find, or how we find an entry once we know what bucket it's in. To do this, we essentially just index keys to the file offset within the bucket. So if we need to look up an account ID, we can map an account ID to a position in the file, so we know exactly where that account is if we have the key. That solves problem 1, finding an entry once we know what level it's in. But we still need to find out what level it's in. To do that, we'll use something called Bloom filters, which is essentially a probabilistic data structure that allows us to determine if an entry is in a given level or not in a given level. Now let's talk about the index in a bit more detail. The index is what maps keys to offsets within the bucket. So this is once we know what level we're in, we want to find where inside the bucket our entry lies. For small buckets, this is a very easy problem. We can map individual keys to individual offsets with no issue. However, for the larger buckets, this is impossible. We need these indexes to be small enough to fit into memory so we can do fast operations, because speed is critical here, and we can't have any of this going to disk. We also need to keep our memory overheads relatively low. So for large buckets, instead of indexing individual keys to individual offsets, we index key ranges based on file pages. Essentially what this is that for every page in a file, we'll say the lowest key within this page is here, and the highest key within this page is here. Then during search, if the key we have is in between that range, we'll take the entire page and load it into memory. Then once the page is loaded into memory, we scan through the page until we find the entry we're looking for. Now because we do this indexing at the page level, we can actually be very efficient about this. This not only, by doing this range index, reduces the memory overhead, but it also allows us to do a single disk I/O operation at all times. Even if we don't know exactly where an entry is within a given file or a page, because hard drives read the entire page at a time into memory, we don't do any additional disk I/O while looking for that entry within the page. So now we've solved the problem of finding an entry once we know what level it's in, but we still need to determine what level of the bucket list an entry could be in. So to do that, we use a Bloom filter. Now a Bloom filter is very similar to a set, except that's probabilistic. It tells you if an element is in the set, or in this case, if an element is in the level or not in the level. Now because this is probabilistic, it occasionally returns false positives. But even though it will occasionally return a false positive, this is still a more efficient data structure. Unlike standard sets, this is a much lighter weight and faster runtime data structure. And since memory overhead is a key constraint here, we'll take the false positives in order to have that lower overhead. Now an important key feature of the Bloom filter is that even though it sometimes returns false positives, it will never return a false negative. This means if we're looking for an entry, it could tell us that an entry that isn't there isn't a level, in which case, in the worst case, we have to go and do an extra I/O operation just to find that the entry we're looking for isn't really there. However, if an entry exists in the level, the Bloom filter will always return true and will never false or give a false negative and say an element doesn't exist when it really does. In this way, we'll never miss an entry, but we might have to do an additional unnecessary disk I/O. Now with these two types of indexes, we need to find balance. Because these need to have low memory overhead, and both these indexes need to live entirely in memory for high-speed operations. So what we did is, if we give these indexes more memory, we have faster lookups. If we have less memory overhead, slower lookups. These are configurable in our current experimental implementation, but we decided on a default configuration that has a similar memory overhead to that as Postgres. We currently view the BucketlistDB as a direct replacement to Postgres, so we thought that this was a very reasonable trade-off since we are trying to remove the Postgres dependency and adding this dependency to the memory overhead to be similar. So here are the results. So for bulk loads, this is when we have a large collection of ledger keys and we're loading them all at the same time. We have a 2.67 times increase in speed over the Postgres implementation that we have currently. For individual key loads, we have a 4.2 times increase. And when replaying the most recent 10,000 ledgers, starting from today, we have a 33 or 32% speed increase overall. Now this does come with some notable limitations. In particular, the experimental BucketlistDB currently does not support offer loads. The reason for this is that offer loads are special insofar that they need to be very low latency, and they need to return the offers sorted by price for things like the DEX. Because the bucket list has offers in many different levels, this is a very difficult query, and so it's currently not supported. However, in the future, we can add additional indexes specialized for offers in particular to alleviate this. Additionally, the BucketlistDB does require more memory than certain SQL implementations. I mentioned that we have the same memory overhead in Postgres. However, there are lighter weight SQL implementations, such as SQLite, that do require less memory. So the final final takeaways is that the BucketlistDB, first off, reduces our disk usage by 45% by completely eliminating the SQL dependency with the exception of the authors table. We can remove a lot of redundant data on disk. Secondly, we have significantly faster I/O by leveraging both temporal and spatial locality. Now, what I mean by temporal locality is that the bucket list, by storing changes in a hierarchical manner, functions very similarly to that of a cache, whereas the smallest buckets at the top are the ones that have the entries that were modified most recently, and since they're the smallest buckets, they're also the fastest to search. Similar to a cache, the entries that were most recently modified or most recently loaded are the ones most likely to be used again. So we have a sort of cache-like temporal locality here that SQL does not provide. Additionally, we have spatial locality. Now, because we're using a range-based index and pulling a page from time from the hard disk, we oftentimes find that the keys we're looking for are next to each other on the page. This means that for a single disk I/O operation, oftentimes we actually find multiple entries that we were looking for, which means that we can often average less than one disk I/O operation per lookup, which is significantly faster than the SQL implementation. Additionally, by limiting the data duplication, that is, by limiting the amount of time that we need to write to SQL redundantly since we already have a bucket list, we can reduce startup time for validators by 50%, which is important in certain applications, like when doing history catch-up or when running a Horizon node. Now, this is still currently an experiment. We have a PR out on the Stellar Core GitHub right now, but it's not been merged in yet. And we still have a few kinks to work out, especially when it comes to the author book. But the initial results are very promising, and this solves a lot of issues, both for Stellar and for blockchains as a whole. Now, I've been talking in the Stellar context, but the two-database approach, a key value store and a Merkle structure, are similar and used in many different types of blockchains, and this does not scale. Not only do we have issues of disk usage doubling, but we also have significant write amplification issues, which would severely limit the TPS of networks going forward once the ledger state of any of these blockchains, including Stellar, reaches a certain size. So we hope that our work here today can help alleviate these issues and help scale Stellar into the next 5 years. Thank you. I think we also have a few more minutes if anyone has any questions.
I have one. If you're going to do something like this, does it make it like more advantageous to add pruning classic? So like add some ability to pruning old data. Because the downfall of this is that really old data is more expensive to look up. So I'll say it again just so the question's hearable. Does this kind of data structure make it more useful to add something like pruning old data? Because the con here is that really, really old information, say at like ledger epoch, I deposit one XLM or something, and 5 years later I ask you to, I don't know, say I want to send it to you, and you have to go load that information. Is that being explored with context to this database, or is there something you can touch on there?
Yeah, so I think pruning old data is a general issue that's not necessarily specific to this database in general. In particular, it doesn't matter how old the data is, if you're limited to a single disk I/O operation, no matter how old it is. Because we're indexing both at the level and also at the individual bucket, we have two levels of indexing. So the first level of indexing, say for instance you have a very old entry, it would be on the bottom level, say level 10. You can go through, you can skip levels 0 through 9 because you can use the Bloom filter to determine it's not there. And so you can automatically go to level 10. And this is still completely in memory because the indexes are in memory. Then once you've narrowed it down to level 10, you then have a secondary range-based index that then also lives in memory and narrows you down to a specific page. And then once you have the page, you do a single disk I/O, and then you scan it. So while there are slight speed decreases for older values because you have to do more, like the indexes themselves are larger, and actually going through the index takes longer, that's an in-memory operation, so that time is significantly less than the disk I/O. And so it is slower, but it's not significantly slower. This is actually significantly better than SQL because we have that temporal hierarchy that I was talking about before, whereas SQL does not have a temporal hierarchy. So a ledger entry that you just used and the ledger entry that you used 15 years ago on SQL is treated the same. Whereas in this, we have some sort of hierarchy. But in the case that you miss the hierarchy, the consequences are not very severe. So it's not proprietary insofar as it's open source, but there's no underlying database. This is all, we don't use SQL, we don't have any dependencies. The bucket list is developed from scratch, we manage our own files, and then the index is on top of it from scratch with like a couple of outside libraries. But there's no underlying database dependencies. This is a database in and of itself.
Thanks, that was great. You talked a bit about comparison to like traditional market tries. Can you talk a bit about? Yeah, you compared a bit to Patricia Merkle tries. Can you like give us a bit more intuition into, you know, like the kind of like the order of magnitude of difference that we're going to see? There's been a lot of discussion recently about how Patricia Merkle tries are kind of like running into a wall in the Ethereum ecosystem.
Yeah, so I think the main difference between the Patricia Merkle tries, which are used by like Ethereum, Solana, and other blockchains like that, as opposed to the bucket list, is the main thread blocking on writes. So in the bucket list approach, because we only ever write to that topmost bucket, and because that bucket is stored completely in memory, we can do not instantaneous, but essentially instantaneous writes with no disk I/O. Now the issue with these Patricia Merkle tries is that you have to, when you update it, you essentially have to wait on the main thread until the Patricia Merkle try is updated, until you can close that interaction and continue. Now, the issue with these stay structures is that they don't have any sort of locality, insofar as it's a tree structure that has nodes and many different files. And when it comes to like these Merkle structures, if you just modify one node, you often have to modify the nodes above it in the tree as well, which means you have to touch many different files, which leads you to the issue of write amplification. And so write amplification is a significant issue when it comes to these data structures. And as these Merkle or these Patricia tries grow, such as the one in Ethereum, you have the situation where you have to do many, many disk I/O operations just to close your ledger. Whereas for us, our writes are all in memory. There's no write amplification on the main thread. Now we have to pay for it somewhere. We choose to pay for it in this background thread by doing things preemptively, so it's not that big of a deal. There's actually a very interesting workshop that came out of this, I think in March, called Where Physics Meets TPS that the Ethereum Foundation puts out. And they essentially showed that once your database reaches a certain size, with the current NVMe hardware, you're actually limited to 220 transactions per second because of this write amplification issue. So it's a very significant issue. Now we haven't seen it yet in many blockchains because these trees grow logarithmically. But if you saw my graph at the beginning, we have a ledger size that's growing exponentially. So even though this tree is growing logarithmically, when an exponent meets a logarithm, you have significant linear growth. So that is an issue that we're going to start to see in the coming future. Oh, yes, it's Where Physics Meets TPS. It was in the Ethereum Foundation talking about the physical limits of the Merkle trials. That's true. So the proof of membership is more involved for these bucket lists because we're not really storing entries, but we're storing changes, right? And so our proof of membership, I believe you actually have to essentially replay the history. Whereas for the Merkle tries, you can essentially see if the node exists or not. So I believe there is a difference in the proof of history work. Yes. But there's there's a pros and cons to each.
Do we have an estimate when this will reach the testnet?
Whenever the PR finishes review. It's pretty close to done. I think the current experimental version, the biggest downfall is that it can't do offers because the DEX has latency concerns that we just can't service with the current indexes. But I believe we should be able to do everything but the offers relatively soon, here probably in the coming months, and then work on the offers in future versions. Any more questions? Or? Well, thank you very much.